Hi, I'm Reethika, and I'll be presenting our system VPNalyzer, which I developed with my colleagues at the University of Michigan to investigate the VPN ecosystem. So over the past decade, the fame and demand for commercial VPNs has been steadily increasing. What was once developed as an enterprise security tool has now found its way into a regular internet user's toolbox. Now, this could be in part due to the numerous reports and news articles we see every day about the internet being tampered with and monitored by various threat actors. All of this has led to an increased awareness of all of these risks. And over time, we noticed that VPNs are increasingly being marketed seemingly as a solution to these issues. Users have started adopting VPNs for protecting themselves from surveillance, to access censored materials, to access work and university resources, especially during COVID lockdowns, among many other reasons. And all of this has fueled the VPN ecosystem to grow into a multi-billion-dollar industry. And this industry, unfortunately, has a bad reputation. And understandably so, because there's been so many reports and stories out there highlighting the deceptive behavior and practices of VPN providers. With that said, it has received relatively little academic attention, with the last reliable investigation being done over 4 years ago. And these previous studies and reports looking into VPNs have all been lab-based and have used inconsistent heuristics amongst themselves, which prevent the monitoring of important issues over time. Now, this is in part due to the large amount of manual work that is usually involved in studying VPNs. And further, these studies were limited in the scale and the types of VPNs studied as well for basically the same reasons. So considering these challenges, it was clear to us that bringing transparency and better security to consumer VPNs requires a completely different approach. So we built VPNalyzer as a system to address these challenges in the VPN ecosystem. First, we wanted to create a robust test suite to rigorously test important features. And this test suite, we wanted it to be extensible as well, because in short, we don't want another investigation done by researchers 4 years down the road to start from scratch. And next, we wanted to facilitate the ease of testing for both users and researchers. We wanted to help researchers move from a lab-based manual testing environment, which is usually clean and has no interactions with other applications, and move them to a real-world measurement. And on the user side, they have varied threat models and various use cases for VPNs, which means different users will prefer different VPN products. So leveraging users themselves via crowdsourcing becomes a solution. So first, I will go over a high-level view of our system's design. So a user will be able to download the tool from our website and run the test suite at the click of a button, which runs our entire test suite, which is containing about 15 measurements from both the user's VPN and their ISP. So once that is done, we get consent from the user to upload the results, which are then analyzed and displayed back to them using a uniquely generated link. So, how do we actually conduct these measurements? The short answer is in multiple phases. So let me just take an example of one of our tests to explain the different phases. So let's think about how you would detect traffic leaks during a sudden tunnel failure. Now, conceptually, how you would simulate this is to basically create an allow list of hosts that are typically needed for this test and block all the traffic except to and from the hosts on the allow list. So this basically causes a tunnel failure because the machine would not be able to connect to the VPN server. So if the VPN's leak protection is effective, the traffic to the hosts on the allow list should also be blocked. Now, this, while it seems straightforward, it demands complex platform-specific implementations, which we do in three stages. The first of which is a bootstrap phase, which takes place when the user clicks the button to start the test. And in this phase, we request administrative privileges and lock the firewall state and initiate sessions that need to start in the ISP phase. Next, we ask the user to turn on the VPN, and then the test suite begins to run. So for this particular test suite, it first has an initialization phase where we set up necessary components for the test, which are again platform specific. So on Linux, that would look like adding new chains on the IP tables. On Windows, we log the PowerShell and the net security versions. And on macOS, we check if the PF or the packet filter allows us to add custom anchors, and we then enable the PF and obtain a token that's needed to reverse this. We then log the firewall state again before we make any changes. So let's get into the changes then. We create an allow list that I mentioned before, and we add the hosts that are needed for the detection of the leaks for this test. So for this talk, I'll be focusing just on the first one, which is the RipeStat data API endpoint, to which we will send a what's my IP data call during the test. So once we create the allow list by resolving all of these domains and adding them to the custom rule set, we modify the firewall and apply our custom rules to induce tunnel failure without resetting the pre-existing rules. And we then log the firewall state again. So once our rules are applied, it would block all traffic to and from any host that is not on the allow list. So this means that there can be no communication to and from the VPN server. So we can then move on to the detection phase. We conduct the leak detection mechanism for about 120 seconds, which ensures that there's more than enough time for the VPN application to diagnose and act upon the tunnel failure. So to detect any possible leaks, we periodically query the RipeStat data API endpoint with the what's my IP data call on both the IPv4 and IPv6. So if some data leak protection exists, all of these queries would time out. But if there's no such data leak protection, or it has a bad implementation of it, the query will go through the ISP and reach the endpoint and return the user's ISP IP, which is the case that's depicted in the figure here. So with this measurement, we cannot confirm if the VPN's leak protection mechanism is completely effective or bulletproof. Rather, we look for leaks in the implementation, and we measure the failure to protect traffic during tunnel failure. And I want to mention that we take another step here at this point to validate our results in case the VPN is governed by a stateful firewall on the user's machine, and we are unable to flush the states and so on. So for more details about that, please refer to our paper. So let's get back to the three phases that I was talking about. So once the test using the VPN is done, we nudge the user to turn off the VPN, and which then runs the test suite again. So for this particular test, that would just mean logging the firewall state, because we don't need to conduct this measurement in the ISP phase. So this is the generalized workflow for one experiment. When the user starts the test, we do all the bootstrapping via the ISP, and then we ask the user to turn on the VPN. We then run the whole test suite with all the measurements sequentially. And then we notify the user to turn off the VPN and run all the relevant measurements again on the ISP connection. And we conduct this process in 3 stages and run the same tests from the VPN and the ISP, because it's necessary to do so to confirm and corroborate our observations. And new tests can be easily added to this test suite as long as it can work in these 3 stages. So the tool at the moment contains 15 tests or measurements, which we divide into 3 main umbrellas. We test for various aspects of service, we test for misconfigurations and leakages, and some security and privacy essentials. So after developing the tool, we put VPNalyzer in practice to evaluate the current state of the VPN ecosystem. So to that end, we tested 80 popular VPN products ourselves, and we found several previously unreported findings. And I'll talk about just a few of them here today. So one of the biggest issues we found was traffic leakages, right? The first thing we found that even though IPv6 is not supported by VPN providers, uniformly, we find that 5 VPNs even leak IPv6 traffic directly to the user's ISP by allowing the traffic to go through the ISP IPv6 link. And our university VPN was also one of them. And we reported this to them and saw that it was fixed. So, and alarmingly, when we measured traffic leakages during tunnel failure using the measurement I just described, We found that 26 VPN providers, which is 1 in 3 of the VPN providers that we tested, leak traffic to the user's ISP upon tunnel failure. And this is in their default out-of-the-box configuration, which is when you just download the tool from their website and enter your credentials and just run the tool. And this is especially worrying because such a tunnel failure can be induced by any motivated network operator or ISP that's targeting a particular user. And when that happens, 18 of these VPNs would just simply leak all traffic to the user's ISP, and 8 of them leaked just the DNS traffic, possibly in an attempt to facilitate reconnection, but that results still in users' DNS traffic being leaked to the ISP at this point. Next, we went another step and tested a set of VPN providers in a custom, more secure setting. We did this by turning on all the relevant security and privacy options that were given in the VPN application. And we still found that 10 VPNs still leak traffic upon tunnel failure. And the important thing is, though this feature is called different things in different VPN providers, we saw that 6 out of the 10 in this list had the recognizable kill switch feature enabled. We filed responsible disclosures regarding our findings, regarding all of the traffic leakages to the relevant VPN providers. And when we were doing our testing, we also found that 2 VPN providers in particular were configured in such a way that they only acted upon browser traffic. And importantly, they didn't mention this explicitly when you turn it on the application. And they allow all the non-browser traffic to be exposed to the ISP. Next, we found that the support for certain security and privacy features that we measured were not uniform across different VPN providers. For instance, DNS resolvers belonging to only 54 providers supported DNSSEC validation, while only 26 providers supported query name minimization. And moreover, we found that 14 VPNs use the Mozilla Canary domain to turn off DNS over HTTPS for Firefox users that get this feature enabled by default on their browser. Now, we specifically report this, and we studied this because Mozilla rolled out DOH by default for its users in the US. And VPNs turning this off silently without notifying the user creates a potential mismatched expectation of privacy. So we contacted these VPNs to see why they were doing this, and the answer we got most often is that users can still go ahead and opt in on the browser, on the Firefox settings, or that they conduct this kind of like turning off DOH for DNS filtering or to upgrade VPN performance. But again, since users are not notified about this, they would not be able to take any steps to remediate it if they need to. And more importantly, users may be expecting a certain guarantee of privacy while using Mozilla Firefox, which has now been silently disabled. And there are many more findings which you will find in detail in our paper, but I want to talk about, apart from these findings, we also took several efforts towards our ultimate goal of making the VPN investigation easier and helping users make more informed choices. So to that end, we worked with Consumer Reports Digital Lab, and they independently deployed our VPNalyzer tool as the first in a line of series of investigations to provide recommendations for their users. And this also served as the first real-world evaluation of our tool. And today, we are launching the beta version of our tool in this link during NDSS, so you should all be able to download and test it out. And our ideas for the future are basically focused on our ultimate goal of improving the VPN ecosystem by leveraging crowdsourcing. And we're planning to expand this to a more public crowdsourcing phase with the aim of bringing systematization to testing VPNs from different regions, to investigating more local VPN tools, and so on. So I encourage you to download it and test it out. And yeah, we'd be really happy to get the feedback from you. So yeah, thank you. And with that, I'd like to open the floor for questions.
Thank you very much.